everyone, I am Miss Hu, your physics teacher. In this video, we are going to go through question 6 of this paper. Question 6 is from Unit 3, Waves, focusing on thin lenses. In this video, we are going to do an immediate comparison of our answer against the mark scheme to make sure that we have fulfilled what we need in order to maximize the marks that we can get in this question. So here's question 6. A page of printed text is placed 18 cm from a converging lens of focal length 35 cm. Figure 6.1 is a scale diagram of the arrangement with each of the two principal focuses, which are the focal points, of the lens labeled F. So if we look at figure 6.1, as you can see, here's the converging lens. The page of printed text is over here, and these are the two labeled principal focuses. Also in this diagram, they've given us the scale. You can see that they've labeled 5 squares as 5 cm, both horizontally and vertically. And they've also labeled the distance of the page of printed text from the center of the lens, and that distance is 18 cm. If you look at the scale, you can see that across 5 squares, it's 5 cm, which tells us that every square is 1 cm, whether horizontally or vertically. They've also told us in the question here in A, a length of 1 cm on the scale diagram represents an actual length of 5 cm. If you have a printed version of this paper, you can measure the distance across 5 squares and you'll find it's exactly 1 cm. And that's what it means by this statement. If you measure in real life, it's 1 cm, but this represents an actual length of 5 cm. So every 1 cm is 5 cm. Question A1. By drawing on figure 6.1, locate the image of the page produced by the lens and label it I. This question is worth 3 marks. So what you need to do is draw in figure 6.1 the ray diagram and the image formed. Now, this software that I'm using on my computer does not allow me to draw straight lines, and you need to draw straight lines in this ray diagram. So you draw with a pencil and a ruler. For me to show you this correctly, I can't use this software, so I'm going to switch to a whiteboard software that allows me to draw straight lines. So I've pasted in this whiteboard a copy of figure 6.1, and I'm going to show you how to draw the ray diagram. Now, whenever we draw a ray diagram for a lens, we need to draw at least 2 light rays, and the intersection of the refracted rays is where the image would be formed. You can actually draw more than 2, but I wouldn't recommend it, because if you drew more than 2, let's say you draw the 3 light rays and you have trouble getting all 3 light rays to intersect at the same point, you're not going to get full marks. You're going to get very frustrated, and then you're going to spend too much time trying to fix your diagram to try to get the same intersection point. So I suggest just draw 2, get that single intersection point, and then move on to the next question. So for this example, I'm just going to draw 2 light rays. So we're going to draw 2 light rays starting from the same point. In this case, you can choose to draw from the top of the printed page or the bottom of the printed page. I'm going to draw from the top. We're going to use the arrow function. Let me just change the color of the arrow so that it's easier to see on screen. This is not where the arrow should be. Let me just move that. Okay, we're going to start the arrow from the top of the printed page, and this arrow goes up to the center of the lens, like so. So whenever we draw the rays in a ray diagram, you should draw them as arrows to indicate that they are light rays. This light ray is traveling parallel to the principal axis. Any light ray that is parallel to the principal axis, when traveling through a convex lens or a converging lens, it will travel through the principal focus. So I'm going to make another arrow here. From the end of this arrow, this light ray now is going to travel through the principal focus, like so. I'm just extending this beyond the diagram so that it doesn't snap to the edge of the frame because that's what this software tends to do. So remember that you must have the arrowheads, one before and one after. The second light ray that we're going to draw should emerge from the same point as the first light ray, but this one is going to travel through the optical center of the lens. Any light ray that travels through the optical center will continue to travel in a straight path to the other side of the lens. Now, just to make this diagram complete, there should be an arrowhead on the line before the lens as well. So remember, there's always one arrowhead before the lens and one arrowhead after the lens. The arrowhead is important because this indicates that they are light rays and not just random lines that you're drawing in the diagram. So now we've got our two light rays. To get the image, we need to find the intersection of the two refracted rays. That means the two light rays that have gone through to the other side of the lens. But as you can see in our diagram, the two light rays we have drawn on the right side of the lens will not intersect. You can see that they are diverging, which means they are actually getting further and further away. There will be no intersection on the right-hand side. Does that mean there's no intersection at all? No. If you look at the light rays, you can see that if you were to extend them both backwards, they will intersect on the left-hand side of the lens. That means behind the page of the printed text. And that's where the image would be formed. So using your ruler, what you're going to do is you're going to extend these two light rays to the left. But every time we do an extension to the back, they must be dotted. So for this diagram, I'm just going to draw a line. Let's make this dotted. And this line should be a straight line from this line all the way to the back. So you just use your ruler and extend it backwards. Now I'm going to start the line from here just to make sure that this is a straight line, because sometimes when I start the line in this software directly from this point, it's not exactly a straight line and we're not going to get the correct answer. So I'm just going to adjust. So I've adjusted this to make sure that this line is a straight line along this ray path. We're going to do the same thing for the other line. So I'm just going to copy and paste. Okay, I'm going to start from here just to make sure that we have a straight line extending backwards. So now, as you can see, we have the intersection point here, and this is where the image would be formed. As the question said, we need to label this point as I. So we're going to label it. I'm just going to put some text here. It's important to label because, for one, the question has requested for it. And secondly, if we don't label it, we are not showing the examiner that we know this is where the image is formed. We can't assume the examiner can read our minds that, yeah, the intersection point is obviously the image. No, never assume the examiner is going to assume. You must label it clearly because that's what the question asks for, and you have to show clearly this is where the image is formed. I'm going to make the label a lot clearer. Let's use a serif font. We're going to make this bold. Let's change the color to blue. Okay, this is blocking. Let's just remove that. All right, and let's make this font bigger so that you can see the label. In addition to labeling the intersection point I, we can also draw the image out. Now, how do we draw the image? We just need to draw a vertical line from the intersection point down to the principal focus. So I've got a line here. Let's just move the line. Let's make this vertical. And extend this to the intersection point. I'm just going to shift this to where the intersection point would be, which is around here. Now, anytime the intersection point is formed with dotted lines, the image you draw should also be dotted. So I'm going to change this to dotted. The dotted image indicates that it is a virtual image. Now, let's check our ray diagram against a mark scheme. So, based on the mark scheme, 2 marks are given for any two of these following rays. Ray from the top or bottom of the object, so the top or bottom, parallel to the principal axis, and it goes through the principal focus on the right-hand side. You could also draw a straight ray from the same point on the object through the optical center, or a ray that comes from the left-hand focus through the same point on the object, and then comes out parallel to the principal axis. So if you can recall, these are the 3 light rays which you need to learn about when you learned about the convex lens. My recommendation to my students is always to draw the first 2 light rays. Not that the third ray is wrong, but the third ray is a lot more difficult to obtain the intersection point with. So draw the first 2, it's a lot easier. In our case, we have drawn the first 2 light rays correctly, so parallel to principal axis and goes through the principal focus. That's 1 mark. And the second light ray goes straight through the optical center. That's the second mark. So any 2 of these light rays. The third mark is given for extending the light rays backwards, and as I mentioned earlier, you need to label the image. So we have the rays traced back to intersection and the intersection or image label I. So the rays traced back to the intersection, and with the label I, this gives us the third mark. And that's how you get the 3 marks for this drawing. Let's move on to the next question. For the next question, using figure 6.1, determine the actual distance of image I from the lens. To get the actual distance, what you need to do is you need to use your ruler and measure the image of I from the center of the lens. That means the distance from our image to the center of the lens. So I've drawn this on screen, but I can still get the answer because we already know from the scale, every square is 1 cm. So we need to get the distance from the image up to the center of the lens. We can count the number of squares between the image to the center of the lens. So in this case, I'm going to play it smart. I'm not going to count all the squares because the diagram has already labeled for us the distance between the page of printed text to the center of the lens, and it's given to us as 18 cm. If you count the number of squares, you'll get exactly 18 squares where it's labeled 18 cm. Now, in addition, the question has also told us that the focal length is 35 cm. As indicated here, the focal length is 35 cm. This means that the distance of the principal focus F from the center of the lens is 35 cm. So that means that the distance from this principal focus F to the center of the lens is 35 cm. So I'm just going to count from F to where the image is formed. So you can see that there are 3 squares. 1, 2, 3. So that gives us a total of 38 cm as the distance of the image from the center of the lens. Now, for some of you, when you draw this in your own diagram, the number you get might be slightly different from mine. Provided that it falls within the correct range within the mark scheme, you will still get your marks. So I got 38 cm, so I'm going to write that. 38.0. I'm adding a 0.0 because it's a habit. Whenever I write any measurements, I always follow the sensitivity of the instrument used. That means if the ruler has 1 decimal place, I'll write up to 1 decimal place. Let's just have a quick check against the mark scheme. And as you can see within the mark scheme, there is a range of numbers. The accepted distance is between 35.5 cm to 38.5 cm. So as long as you have drawn your ray diagrams correctly and the image distance obtained falls within this range, you will get your full 2 marks. So if you didn't get the numbers within this range, you can still get 1 mark. For example, if you made a mistake, you forgot to count it to the actual length of 5 cm, you just use your ruler measurement and wrote exactly as what you got. That means 7 point something cm. They will still give you 1 mark. Or if your image happens to fall outside this range, they will still give you 1 mark as long as it's within 35 to 40 cm. So in our case, we got exactly within the range. So we've got full 2 marks. Now let's move on to B. Converging lenses can be used as magnifying glasses. State whether the image produced when a lens is used as a magnifying glass is real or virtual. Explain why. So this relies on your knowledge about how converging lenses are used as magnifying glasses. If you can recall, when you use a magnifying glass, the image formed is virtual. In fact, the diagram that we've drawn in figure 6.1 is exactly how a lens is used as a magnifying glass. Let's just review the figure again. When you use the convex lens as a magnifying glass, you normally have to place the object quite near the lens, that means within the focal length, and you will get a larger virtual image. So here's what we're going to, right? The image formed is virtual. And to explain why, let's just keep it simple. We'll just further elaborate about virtual images. So virtual images cannot be projected on a screen. Let's have a quick check against the mark scheme. So as you can see, you need to write it's virtual as well as one further explanation. An answer from any of these options are accepted. You can say that the image cannot be projected on the screen, or you can say the light ray does not pass through the image, or that the light only seems to come from the image, as seen in the figure that we've drawn. You need to write both out before you can get 1 mark. So we've already got this, we've got the 1 mark. Question C. Suggest how someone who is long-sighted may benefit from using a converging lens. So this is a 2-mark question, which requires you to be able to explain a little bit about how long-sightedness is corrected using a converging lens. So in my answer, I'm going to write it this way. So in my answer, I'm going to write the first one, where I explain a little bit more about long-sightedness. So in long-sightedness, the light rays will focus behind the retina. So how the converging lens can fix the long-sightedness is by focusing the light rays forward so that the image can be formed on the retina or the back of the lens. So I've chosen to write this statement so that in my second sentence, it's just about the correction of the light rays with the converging lens. So the converging lens will converge the light rays forward to focus on the retina. So personally for me, I like to have a link between the two statements so that it makes a lot of sense when you're reading the answers to get the full 2 marks. So let's take a look at the mark scheme straight away. The first mark is given for any of these options. You can talk about how the long-sightedness focuses the image behind the retina or the back of the eye, or that the long-sightedness produces a blurry or fuzzy image of close objects. Or you can also say that the converging lenses reduces the focal length, or that the converging lens puts the image further away from the eye. And that's how we can get the 2 marks for this question. And that's how you solve question 6. If you'd like to find out how to solve the other questions in this question paper, please refer to the playlist in the video description. Happy studying!